Okay, so let's proceed with the introduction for the course. And remember, the introduction is not going to be tested in the exam. So this is just for our motivation. I mean, is the course relevant? Why are we studying this? And how? What are the current issues in VLSI circuits design and so on. Okay, so let's just quickly go through this, just looking at some of the motivation of the course. So let's slideshow. Okay, so present, past and future. Why is designing these ICs different today than it was before? Will it change in the future? Actually, I think this slide is quite old. It's from Rabi's book. Okay, so it's quite old, but I think it's still, some of the content is still quite relevant. We'll see how it goes. Okay, so as you might know, I mean, maybe you at Intel, you're working on a more, a more advanced process compared to this one. I mean, this is a 1832. It's a classic, very old model. I'm here in Singapore. I'm using a 5 nanometer TSMC process, the latest process. So it's a little bit different, but the main concept is still there. Okay, the main concept is still there. So this is the first computer ever built, which is in 1832, more than 100 years ago, and the cost there we see is 17,000 pounds. Okay, the first electronic computer in 1946, huge. So if you compare now, you can put the whole thing, whatever you are seeing in this picture, in your hand, basically, right? As a smartphone. The transistor revolution, the first transistor ever, the Bell Labs 1948, is a very important milestone, I would say, for VLSI design, because transistor is the basic building block of any chips, analog chip or digital chip. If you don't have transistor, then we cannot do this kind of complex chips. Okay, so 1948 was the first transistor. And then you have the first integrated circuits. Okay, so previously it was a large transistor. I mean, maybe the size of your smartphone. Okay, one transistor the size of your smartphone. So 1960s, around 10-12 years after, then you have a kind of a small but still quite big chip. Okay, using bipolar transistors. 1971, 10 years after, you have the first Intel microprocessor with 1,000 transistors that could fit basically in your hand, right? 1,000 transistors. So previously one hand, one transistor, and then it gets smaller and smaller. 1971, you have 1,000 transistors in your hand working at 1 megahertz operation. Then you can have also, afterwards, you have the Intel Pentium 4. So Pentium, I don't know about your generation, but my generation, I can still remember using Pentium. I think during my undergraduate, during my undergraduate, a long time ago, we used to buy Pentium PCs. Moore's law. So what is Moore's law? Moore's law is basically the saying that the number of transistors on a chip double every 18 to 24 months. He made a prediction that semiconductor technology will double its effectiveness every 18 months. Okay, and it's still true today, in some sense. Okay, it's still going on today, but we will see. Now it's going 5 nanometer, and next year they are targeting 3 or maybe 2 nanometer process technology. And I don't know what's the limit. Okay, I don't know what's the limit, but I think, in my opinion, eventually we are going to hit a dead end on the smallest feature size of the transistor. Okay, so as we can see there, the number of transistors basically double every 18 months. the evolution in complexity. Okay, I'm not going to go through this one. Transistor count. So as I said, this is a quite old slide. In 2010. Okay, so in 2010, let me see if I can write something here. Okay, forget it. Discard. Okay, so basically the same thing is what Moore's law is saying, that the number of transistors double every 18 months. So let's go on to the next one. Again, the Moore's law concept. Okay, transistor on the works at double every 2 years. Okay, 18 to 24 months. Die size growth also related. So remember what it means by the die size. So basically, the integrated circuits or the chip is actually manufactured on the die, right? On the die. So the die size actually remains quite constant there. As you can see, the die size remains quite constant as compared to the number of transistors on chip. 7% growth per year, 2 times growth in 10 years. Okay. Operating frequency. Okay, we are operating frequency. So during when they did this slide, they predicted that the operating frequency of your computer or your microprocessor will double every 2 years, and by 2010 you are working on what is that, like 10 gigahertz PC. Okay, which is not true today, right? Now we are in 2020. What is the operating frequency of your chip? Maybe around 2 to 3 gigahertz. Okay, so it's not up to 10 gigahertz, and mainly because of power consumption. You simply cannot push up your frequency to 100 gigahertz and so on, at least using the current technology. Okay, power dissipation, you can see the power dissipation is keep growing up every year. Okay, we are going to analyze more about the power, dynamic power and static power, and it becomes a very important issue nowadays. In 2020, we are talking about mobile devices, okay, mobile operations where power consumption is a major major characteristics, or a major part of a design criteria instead of delay. Last time we talked about how speed your chip, but now how much your chip consumes the power. Okay, next. Power will be a major problem. That's what was predicted before, and yes, today you can say that power is a major concern in modern design. Power density, okay, power per area. So you can see there. Okay. So he's saying that by 2010, our chip will be as hot as the nuclear reactor. Is it true? Well, it's not exactly true in 2020. So people and the engineers, the scientists, they have found a way, probably how to mitigate the power issue so that it doesn't become a nuclear reactor or rocket nozzle. Okay, it doesn't happen today. Okay, so not only microprocessors, also you are talking about cell phones during this time. So I don't know if you've seen this kind of cell phone. I can still remember we used to have this kind of phone before. I don't know about your generation, but now cell phones are now called smartphones, and they look quite different. So what are the challenges in digital design, and is it still relevant today? Okay, so this is quite important. I mean, to see as an engineer, as a scientist, working in chip design, what are the issues that we are expected to tackle, to face, and today, so if you talk about time to market, okay, time to market, yes, today, okay, like the company I'm working for, I mean, we have product that we ship out products every 3 months. So we have a deadline to tape out the chip in 3 months. Okay, what will happen if you don't tape out in 3 months? Then your competitor will go in and you lose the market, right? So time to market is still so much very relevant. How to design fast and also with good quality results. Parasitics is also still something important that engineers need to analyze. Parasitic is still there. Okay, no matter your 5 nanometer FinFET or whatever, parasitics will still be there, and how to model the parasitics, how to be aware of it, what it means by the parasitics in your VLSI circuits. Millions of gates, yes. I mean, now you're talking about millions of instances, okay, cells, standard cells, and so on. Power is always an issue. Today, I mean, now it's more important. In fact, power is probably more important than delay. Okay, if you are working for, if you are doing a mobile chips, then power is more important than delay actually. Okay, reliability is another important one even today. How to make sure that your chip is actually relevant, is actually reliable. Okay. So what else we looking here? So productivity trends. So productivity trends here, we are looking at complexity logic transistor per chip versus the productivity transistor per staff. Okay, so basically it's saying that the chip growth outpace the number of staff, that number of engineers that we produce every year. Scaling, why we do scaling? Okay, we are talking about in this class, basically we are looking at the quite old but still, I mean, for learning purposes, okay, we are looking at 25 to 50 nanometer or 0.25 micron technology. Okay, 0.25 micron technology. It's an old one, but it's still it's good for learning. I mean, you want to understand the concept, and it's still quite relevant. And there are people still fabricate the design of the chips on 0.25. In fact, okay, not everybody has the not everybody have the what you call it, the capacity, the ability to go for latest 5 nanometer design. Okay, only if you do mobile, you are concerned with power, with delay. Okay, then you go 5 nanometer. Okay, but some companies, they are also still working with 180 nanometer, 250, 65 nanometer, and so on. So so why the scaling? Okay, we are talking about 250 nanometer 20 years ago, maybe around 20 years ago, 250 nanometer, and now 5 nanometer. So from 250 to 5 nanometer size of the transistor, right? And why we are doing the scaling. Okay, so this is quite important to understand what it means by 5 nanometer, and what's the importance of scaling, in fact. Okay, so here we can see that actually the cost of function decrease when we do the scaling, but then if you do scaling, then how to design chips is more and more functions, because now we have more area to do the design. Okay, but the design engineering population does not double every 2 years. So what about the design methodology? How can you leverage maybe machine learning and so on, so that we can actually use or implement the extra functions? Okay, maybe parallelism, implement more functions in the chip because we have more area. Okay, hence there's a need for more efficient design methods, and this is true even today. Okay, so let's look at the design abstraction level. So the lowest abstraction is the device. We're going to look at this, a transistor device. You put the transistor together, you get a circuit, 2 transistors, you put the circuits together. I mean, you put the transistors together in a certain way, you get logic gates. You combine the logic gates, you get a module, and you can combine the module to create, let's say, microprocessor or some functions, and then you can create the system level. Design metrics. Okay, so how do you know if your design is good or not? What is the criteria to evaluate the performance of a digital circuit? Okay, so here we look at the cost. How much did it cost to fabricate, maybe from design all the way to fabrication of the chip? How much did it cost? Is it reliable? How long can it last? Is it scalable? Change technology, can we easily redesign or redo the block for new technology? What about the speed of the chip? Is it fast? Okay, because if you are not fast, somebody else is faster, they're going to get the market, right? So you need to be competitive on the speed and also the power, energy related to the battery, right? If you can have a low power design, then you use less energy. Cost of integrated circuits. So how much does it cost to design and fabricate your VLSI chip? Okay, and of course the answer is of course very expensive. Okay, only very few companies that are able to. We are talking about Intel, Samsung, and you know some big companies, and you know the foundry, the fabrication facility to build that cost maybe tens and $20 billion. Okay, just to build the fab facility. Okay, not to mention the engineers required, the scientists required, and so on. So it's a very expensive endeavor actually for integrated circuit design. Okay, die cost. Okay, so what is a die? So basically, a die is a round silicon basically, and then you have the wafer is a round silicon, and then you can cut through into partition the wafer and get the die. Okay, let's see. Okay, so cost per transistor goes down. Okay, not going to go through this one. Yield calculation, not so important, but you know you can see what it means by yield. So yield is basically from your wafer, how many die is good die and how many will be not good. Some examples, I think I'm going to skip this one. Okay, so the summary. Okay, let's look at the summary and see if we are motivated or not to do the course, right? I mean, is it important course? Is it still relevant today? What you're going to learn? So first of all, I'm going to say that the course is not so easy. I mean, there's a lot of mathematics involved, physics, logic analysis, and I would say it's one of the more challenging courses for our program, also for the master program. Okay, there's always somebody repeating the course. Okay, there's always somebody, but most of you will pass. Okay, hopefully we'll see how it goes. We need to get the motivation to do it, right? I mean, is it important? Is it relevant to your career, and so on? So if you're focused on the career on chip design, you want to have a career in chip design. Of course, this the content in this course is really relevant. Okay, the mathematics and so on to understand. When you do the actual engineering design, you understand the underlying concepts. Even though maybe you're not going to do the exact same thing what we are doing in this course. Okay, even also this course we are considering quite old technology, but the concept is still the same. Okay, so for me, digital chips. Okay, we are talking about digital chips here. Digital chips. Now it's 2020. Is it still going to be relevant in 20 years, in 30 years? Okay, that's the question, right? I mean, but for me, yes. I think in 20, 30 years, people are still going to use integrated circuits, digital chips. Okay, and at some point, the future technology, 5 nanometer and so on, at some point is going to stop. And people will come up with some new technologies. But the underlying concept is still the same. If you're talking about silicon, transistors, MOS-based transistors, is still the same concept. Okay, so digital chips have come a long way and still have quite some potential left for the coming decades. And some interesting challenges ahead is getting a clear perspective of the challenges and the potential solutions. Okay, so understand the underlying concept and to appreciate what are the challenges and what are the issues within the chip design environment or chip design work. Understand the design metrics that coverage digital design is crucial. Okay, how to produce chips that cost less. Okay, how to make it reliable, how to make it fast, how to have low power, low energy. That's the key. Okay, because if you are able to find the fastest chip doing the same function, the fastest chip, the chip with the lowest power, that can last the longest battery, okay, then you're going to have the advantage in the market. Okay, so I think that's it for the introduction, and for the next lecture we go right into the material, the main part of the course on MOS transistors.